Welcome everyone to this tutorial today. I'm here with a couple of colleagues. My name is Andreas Glamfeldt. I'm the head of software technology at Biosero. Together with me I have Lucius Kemp, who is the scientific director, Ben Matthews, who's the analytical technology director at Pfizer, and also then Ash, which is team lead for the European field application scientist team. So I'll hit off first by talking a bit about what we're doing on the software front at Biosero, talk a bit about AI and also the reality we live in the labs, and try to be a bit pragmatic on it and not just ride the hype of AI. So just to start with, I mean, all of us have seen all the advancements that has come today and a couple of months ago and is increasing even faster as we go forward in terms of AI, especially the LLMs systems that are helping in the dry lab and the hypothesis generation out there. What I do think is that it also then pushes the bottleneck down to the wet lab where we actually operate. So we become the bottleneck in terms of validating all those hypotheses and generations of candidates potentially. And we try to address that with our platform. I will not pitch anything in terms of our software today. I will just speak briefly about what we do and what we think. And I guess being the bottleneck, you still need to have validated evidence of what you do so you can actually validate and feed that back to the LLMs so you can do the next hypothesis generation. So I think that's important. If we then just look back quickly on history, we started with the automated platform a couple of years ago, and then it went to connectivity with all the instruments and devices. Then we started with lab orchestration, and from that then advanced workflows. And I think now the next step is the AI driving that automation. But the question I would like everyone to bring back to your companies or home is on whose terms? Because right now it seems like everything is AI and we trust AI with everything. And is that the case actually? So based on studies or actual customer data back from 24, we know that automation itself increases the downstream process and assay development by 75%. It increases the capacity of the equipment with 400%, and it also then expands the productivity by 200%. All of that is only just by automation, but if you then put AI on top of that, that becomes really critical that you have a stable platform that you run on, because devices are messy. They are developed for manual experiments and not automation, many of them. Some of them are quite good, but still there are instruments that are not AI ready or automation ready. So what do I think about that? I think that AI in our world in the wet lab is assistive. It's not autonomous. It needs to be a human in the loop. It's really good at troubleshooting, recognizing patterns, and making the process and uptime and throughput of the wet lab great if applied correctly. I think the 80-20 rule also applies here. And we know that by trying it out in our proof of concepts, that 80% is probably automizable based on AI doing it. But the last 20%, the edge cases, the regulatory, everything that you all know happens in the lab, the effort of doing those last 20%, is that worth it? That's the question. And I think the same transformation that was done with digitalization many years ago in a lot of industries also applies here, because it's still people and process. AI will accelerate any process, good or bad. And also organizational dynamics, the regulations that you have. So technology in isolation is probably not the biggest hurdle here. So if we just briefly go through the bottleneck in the wet lab again, I think the generation of drug candidates will exponentially grow. That brings the bottleneck down to the wet lab. The wet lab will become the compute cluster that needs to run 24/7. I still think with humans in the loop. And a trusted automation will become indispensable for R&D at scale. But it really comes down to how you handle all of the devices and the real automation that happens in that execution cluster, if you call it that. And if you look at the roadmap that has been at everyone's agenda for the last couple of years, I think that the journey is the same. Maybe the destination has changed a bit. I think that we came from full automation to something more like trusted hybrid intelligence at scale. I still think that's a change of destination, but the journey is still the same, and the challenges will be the same for everyone. So what do we do then? Just briefly, of course, as everyone else, we're using AI in our development processes to become much faster in developing new functionality and expanding our platform. And we see that we can do that at much higher pace than we could before. And that's changing for every week because of the development of LLMs and AI models. So that's really helpful. And what we're doing on the AI track is introducing AI as an assistive support in our products to keep all the scientists in the lab to be able to run the systems as fast as possible with least amount of downtime. So it comes to error handling, finding patterns, and keeping the uptime of the system, but also onboard people into the system that are new. And our perspective on the lab OS, I mean, everyone wants to be the operating system of the lab. I think it's a downstream problem and not an upstream problem. I think the upstream with AI in the dry lab and when it comes to data is, of course, something that we're looking at. But I think when you can scale, I think many customers will look for ways of putting experiments where they have throughput capabilities, and it might be global orchestration, so they can actually orchestrate stuff between different labs. But then you need to have really resilient device management and be able to scale that. So that's something we're looking at because we have many, many years of experience and scars on our back when it comes to integrating devices. And I think that's the big downstream problem that we're trying to solve, because the upstream problem is with AI easier to solve. So what's being available soon in our products are assistive AI to be able to do quick, you see I'm being waved at now, so I'm soon out of time. And the next generation of our products, which we call Crescendo, is a high throughput platform with human in the loop, AI assistive to keep uptime. And I think the trusted execution will become indispensable for being able to do that, as the R&D of the labs will scale and will be exponentially done by AI. So just quickly, as the last slide, the focus areas for Biosero and me right now when it comes to our products is connectivity, so being the unified control layer across all the systems and instruments and labs. The data, the decision-ready data, to be able to provide data so that AI can help out with the next steps. And I think that on the AI perspective, it's from execution to calibrated intelligence. I don't think that we should fully trust AI. I mean, in the wet lab, it's a deterministic thing, so you don't want to have probabilistic models trying to figure out what the arm should do next. And the partnership. We will still be the vendor-agnostic ecosystem that will build end-to-end automation. And we're looking for strategic partners to accelerate that development over time. So that's what I had for today. And if you have any questions, I'll be in the booth later. And now I'll hand over to Lucius.
Hello. Hi, so I'm going to continue and elaborate a little bit on what Andreas just spoke of, but talk away from the software and go more into the actual automation, okay? So one of the first things I want to do is go back to this slide because I think it's very important. There's a few other things I want to mention about it. And I think it's safe to say that when artificial intelligence came onto the scene when it comes to drug discovery, the idea behind AI was the fact that it was going to help scientists design better molecules, therefore requiring less reactions, less molecules to be made because we were supposed to be able to figure out which ones are not going to work before we went through the whole process of synthesizing, purifying, and testing. But like most things, when you start down the path, reality changes what your thoughts were. It has now turned out that AI is not decreasing the workload on the wet lab, but is actually increasing it further. So we're now developing and designing more molecules on an exponential flow that requires a lot more of compounds to be synthesized and tested all the way through the entire processes. This will probably hold true throughout the entire chemical industry, depending on what field that you're in. So again, this becomes the wet lab is now the area, I don't want to call it the bottleneck, but this is the area now which still requires a lot of shall we say, horsepower in order to meet this demand. So, and the best way to do this, as we see on the bottom point here, is the trusted automation is still king when it comes to providing that type of response to this new directive or this new pull on this technology. Now, the case for automation has never been stronger. We're entering into a new world where it's a new draw, a new pull on lab automation. And the path to getting this is a very, very difficult one. The larger your platform, the larger your automation program, the more, shall we say, potential problems that you can have as you're trying to reach this point. It is full of so many potholes that can easily trip you up and stop you from reaching your end goals. And here's just a few of them that I've listed here. Things like, picking the wrong supplier or partner, whichever you want to call it, putting the wrong team together, having underdeveloped operational concepts. I mean, there are many ways in which you can kind of set yourself up for failure if you're not going about this in a proper way. And I think the beginning, the origin of all of this has to be your operational concept. Now, what do I mean by operational concept? Before we start designing, before we start picking instruments, before we start choosing software, the first thing we have to understand is what do we want to achieve? And the first step in what do we want to achieve is how far or how much do you want to automate? Oftentimes people will either choose an under-automated solution that doesn't reach their goals, or they over-automate, in which case you spend more time, playing with instruments and robot arms and not generating the data that you want. So the way I look at it, if you're following this crawl, walk, run, fly concept, farthest on the end, people, I guess you can even say people just starting out, just a mechanized approach. I just have a liquid handler. I'm just going to use this to solubilize some compounds, whichever, they'll do some reformatting, whatever the case may be. Next level up, automated, where you might want to pull 2 or 3 processes together. Maybe you want to do some reformatting, some heating, some shaking, a plate read, something along those lines. You move into the next level of integrated, where you have an entire, shall we say, an entire workflow that you want to bring together, a particular assay that includes incubation, centrifuge, things of this nature. Usually, integrated process, there'll be what we call a work cell. This is where our GBG software comes into play. And in this work cell, there's some type of transport system, whether it's an arm on a rail or it's the, as everyone is saying now, the biomech maglift systems, whatever the case may be, you're moving samples from system to system. Now, when we come to the fly concept, this is the lab of tomorrow. It's not actually the lab of tomorrow anymore. It actually does exist, but these type of labs are the full-blown, what you hear, the DMTA labs, okay? These are the labs that have the high-throughput experimentation concepts built into it. So high data output, very low input or workload from the humans. Humans are still involved, but this is very, very end-to-end process. Fully automated and fully integrated. Next level up is when you want to go to this autonomous concept. Now, Autonomous pretty much means the system has to be intelligent enough to design or program itself on the fly. For an example, let's say you run several compounds in parallel that you're trying to synthesize, you run the analysis. What happens at the end of the analysis? Either the material worked, the reaction worked, or the reaction did not work, and if it did work, is it pure enough to go to the next step, or does it need to be purified? So all of these can be built into the system to where the system, based on reading the analysis back in, can redirect samples to go in different locations and different outcomes. This is this kind of autonomous flow. Now, all of this is what's needed for these AI-directed laboratories if you're planning to go that far. Now, the collaboration is key for all of this. If you're trying to go to these very large platforms, or even I would call them medium-sized platforms, the talent pool to complete this can be deep, okay? No more can you get away with just having a scientist on board. As we're talking AI, we're talking a lot of data, we're talking engineering feats. So starting at the beginning, what I would say the central point, again, operational concept being center key. But you have to make sure when you're designing your operational concepts, it's not only based on the science, but it's also in alignment with your financial support that you need. It makes no sense to design something that you don't have the financial support to purchase. It must also align with whatever your business practices are and your regulations. Are you a GMP environment? Are you early research and development? What are your site regulations? What are your safety regulations? All of these have to come into play, and it gives you a much smoother transition later. And the next phase up comes when it's now start trying to develop and to implement your system. This is where the science and the engineering and the software teams have to work in conjunction together to develop what you would actually need to be successful. And of course, the commercial side. Now, most people will see commercial and they'll think, of course, as Biosero, we are your providers, your partners, but you also have an aspect of commercialization, because when you put together this plan and you have to go to your, shall we say, your leadership to get the money for it, you have to do an internal sales job as well. So you have to make sure that you have all the information that you need in order to be successful in obtaining the funds that you want to move forward. And of course, the most important piece down in the bottom corner is your partner. And there's not a mistake that I put your partner right next to the Biosero logo. It's because we're the partners for you guys to do this, okay? So another very important aspect is change, okay? Change, and I'm not going to read through this long definition. You guys can read it or Google it. That's all I did. But it is a mindset change that must happen for you to go from the bench to an automated assisted research. So I'm going to give a parable to this to describe this. So I'm going to call this the birth of productivity. And I'm sorry that that picture is so small, but what that is a picture of Ford car manufacturing plant prior to 1913. In this case, it's very hard to see, but there are a bunch of cars lined up in the room, and there are teams that are going around to each car and they're manufacturing, they're putting it together. After 1913, the moving assembly line was invented. The moving assembly line was invented, and therefore this made the transition that has really changed the productivity and changed manufacturing across the entire globe. But in order for them to move from these two windows, there were a lot of changes that they had to make in the way that they do business. The way that they thought about how to handle things, they had to make this transition. Now, when they set out to make this transition, it is reported that they were not trying to come up with a new way that was going to change productivity across the entire world, but they were merely trying to do one thing, and that is to deal with the new demand that they had for all the cars that they needed to deliver. Okay? This is the same kind of ideology that you guys are going to have to do within your respective areas to make these transformations so that you can move from the bench to this type of automated environment. And these are some of the changes. I won't go through those, but these are some of the changes in mindset that is required for you to move to this fully automated world, especially when it's driven by AI. And the most important piece here is the hidden barrier. Many of you have probably already come across these. If you're new to this world, you will. The purist mindset is oftentimes a block to innovation. So what I always say to people, don't think outside the box, live outside the box. You are the ones that have to drive this change and bring about this new era in laboratory research. So when I said to you as far as partner goes, as Biosero, what we do is we've put together an entire technical team to help you along this journey, okay? So we're starting from helping you design your concepts over to our application consultants, and someone that you'll hear from later is the team lead in Europe of our application consultants. I'm sorry, another one down the line here. These guys will help you pull all together all of your specifications and help design your concepts. And then we go over to the solutions architect when we're talking about data flows and orchestration. This is the team that will actually help design and put this in place for you. On into our internal and engineers and application scientists. These are the guys that are responsible for building your systems. And then over into our field application engineers and application scientists. And these are the guys that actually will come out and install these systems at your site, and then do a nice platform handover so that you can hit the ground running with doing your research. Okay. Last slide that I have, I'm going to now turn it over to the next presenter. And I'll pop that up. There you go.
Hi everyone, so I'm Ben Matthews. I work at Pfizer. I work in research and development in Pfizer. In R&D, we are evolving our labs from disconnected point solutions to integrate automation and also to use digitally orchestrated workflows. I'm going to go through why, when we do this, we're integrating science and technology in a structured way, why that is meaningful to our environment. I'll go through the gaps that we see and then some of the things we're doing to address those gaps. Right, so this is the mythical DMTA cycle that we all dream of. Scientist captures their intent in a system. The system orchestrates that intent through the laboratory. The data comes from the laboratory into a centralized database and in a format that can engage directly in AI and extract our scientific intent. It's brilliant. Life isn't anywhere near that just yet. It's not that linear, it's not that simple. So what is it like in real-life R&D? Real-life R&D is really messy, in fact. Real-life R&D, the work goes across functions, it goes across teams, the work happens in parallel, and the work is all interdependent. So we've got work streams that span teams, labs, and locations. We're in development, we're not doing screening. All of our experiments are unique, they're under ever-changing conditions, and human judgment is critical at every stage for compliance and scientific judgment. So we have this messy reality of teams, labs, and locations that need coordinating. Up the far side there, up the left-hand side, we've got the business of pharmaceutical science. So how do we get the orchestration and the automation the outputs of that, up that value chain, up that hierarchy to affect the portfolio and the business operations of our organization? And then on the near side here, on the right-hand side, we've got the science hierarchy. So our deliverables in development are they are materials for the clinic, they are control strategies for regulatory dossiers, control strategies, and they are manufacturing processes that we can scale from labs to commercial manufacturing plants. Those are our deliverables. We do that by breaking our processes down into steps. We break our steps down into unit operations, and we like to model and twin our unit operations from the site, from the lab to the plant. And we break our unit operations down into focus areas to make them more manageable, and then we characterize those focus areas with hundreds and with thousands of experiments. If we miss anything in that entire system, then we've lost context for AI to engage in what it does, and we've also lost the value of the orchestration up and down those hierarchies to extract and realize the value of this technology into the business and into the science. Right, so what happens? When we take these tools, doesn't matter what the tool is, in fact, these are the default failure modes of how we break the tools that we can see in the shop just across the road there. User interfaces that don't match what we do for a living, our experimental intent, manual steps that hide inside automated workflows, and that could be a digital workflow or a workflow at the bench. And then ontologies and integrations. We've got a sea of ontologies and interoperability gaps. That's just with our internal enterprise systems, let alone the 100 different hardware and software at the bench. What this amounts to is a system, an overall system that is not flexible enough to actually carry out R&D as we want it to. For example, it can take months to onboard a workflow or even a variation of an experiment into a system. Right, so what are we shooting for? So what are we going to do about it? The ideal state. So the ideal state looks something like this. We've got scientists that can focus on science. They do not have to worry about the tooling. We are able to orchestrate our work across teams and across silos. We've got full visibility of all of those human tasks and human judgments, whether in a data pipeline, in the office, or in the bench, the wet lab. We've got something that is scalable and resilient. We can scale it through our organization, and it can cope with change as well. And then nothing escapes. Nothing escapes that entire system. So that we don't degrade the context and the value of what we're capturing and the tools that we're using. So I'm going to walk through one of the approaches we're taking to try and address those challenges. I'll break it into 3 steps. Deconstruct our messy reality into atoms. Structure those into a system where we can have lossless handoff between intent and execution. And then what can we do with it? We can now we can separate platforms, and we can have expert platforms where we need them. Right, step number 1, capturing messy reality as atomic tasks. So we've got our business operations, we've got our work streams, we've got our scientific deliverables, we've got what happens at the bench in the wet lab. We deconstruct all of that into atoms. And just as an example, one of those atoms is the humble act of weighing. It's as simple as that. What we then do is we take all of those atoms and we structure them into a graph. We connect those, we assert relationships between all of those atomic tasks so that now those have context, and we map those to our internal systems, whether it's LIMS or ELN or a people, an HR system or a sample inventory system, doesn't matter. And we also map them to external systems. So that could be external standards, or it could be your system. So that gives the content, so the atoms become content, and then the mapping gives them meaning. We can resolve that meaning and give it understanding now. So basically all of those atoms has now a contextual understanding in order to execute. So we've taken those atomic tasks, we can now translate those into a digital instruction without any loss of scientific intent through that journey. So what are we doing? So what we can do with that now is we can separate platforms. We can have a user interface of our choice that is expert in what we want it to do, and we can have a lab orchestration system that only has to be expert at what it is supposed to do, and we can bridge them with the graph to create that contract between the scientific intent and the execution piece. We're doing this in an agnostic and portable way. This isn't so that it's scalable. Right, so let's have a look at the user interface. So now we have prototype user interface that we can run demonstrations with. It's purely focused on our scientific intent and capturing our messy reality. So there we have our user faced with a whole bunch of atomic blocks and their intent. They want to create a contour plot of their unit operation. They can instantly compose those atomic blocks in this interface in any order to capture their intent. So they can reuse, recombine, and they haven't gone anywhere near an execution system to break it. They can capture the business workflows, they can capture the scientific workflows, the process, the unit operations, all the way down to the experiments within one system, and then you can collapse all of that into a digital artifact. And now you can send that digital artifact to a lab execution layer. And the lab execution system only has to worry about being expert at executing that work through the lab. So we've partnered with Biosero around that artifact. And Biosero GBG, we're working on having that artifact as something that can consume and break back into those atomic tasks to execute at the bench. And so GBG can take those atomic tasks and it can dynamically schedule them across labs and equipment layers in series and in parallel. And in doing so, they can maximize the throughput of that experimental package, the speed and the equipment utilization through the labs. But we're not just stopping at automation, we're not talking about work cells, standard labs included. So we want to digitally connect in a workflow the people, the instruments, the data, and the decisions, otherwise we lose the context. So we're building the hybrid orchestration engine with GBG, where we can unify manual and automated tasks. We can interleave those within a single experimental workflow so that every action, every intervention is captured digitally by the system. Doesn't matter if it's manual, doesn't matter if it's automated or instrument-based. And of course, we're not going to stop there either. So in R&D, we have lots of different lab environments. Some labs are highly automated, some just aren't. Some of our work does not lend itself to automation. So we have to accommodate these different lab environments as well. So we're working on 4 different dispatch modes to allow to just those different working environments. If your protocol is robust and reliable and lends itself to automation, you can choose to send it directly to automate and orchestrate through the system. But there's some circumstances where we need to commandeer either a specific piece of equipment or a specific lab location or even a specific person with a specific set of expertise into that workflow. And so the user interface, the external user interface of our choice, we can specify the resources we want, and Biosero, when it orchestrates the work through the lab, can dispatch and commandeer those resources into the workflow. Another example of a dispatch mode is a hold point. So in the user interface, we can specify a hold point. That could be for safety reasons, compliance, or just judgment, some human judgment involved in the workflow. And when it's orchestrated through the lab, Biosero can introduce the hold point into that experimental workflow. And then the last one, which is possibly the most ambitious one, is we don't always know what we're doing when we go in the lab. A lot of work actually is very exploratory. We don't know how the materials are going to behave. So we want a dispatch mode where you can walk up to the bench, you can run your scientific work in a very natural way where everything you're doing is captured and digitized as you do it. So that you don't miss anything, nothing escapes the system. If you want to do that again tomorrow, someone else or something else, automation, can reproduce that with a digital precision. So these are the dispatch modes we're working on. Coming back to those labs, some of our labs are less mature with automation than others. We can use these dispatch modes as automation matures and comes onto the market, and we can introduce it into our labs. We can use these dispatch modes to onboard new automation as it develops and into our workflows, but we don't have to go back and write the workflow from scratch. We can just choose our user interface to include that piece of new hardware into the existing workflow. So it helps us with the change management process of evolving our labs. Okay, so what does the DMTA cycle look like now? So we have, sorry about the graphic down the side there, that's a scientific hierarchy. We have now a digital twin of our messy reality, of our scientific hierarchy with the unit operations and digitized process. So our project lead now can engage in a digital twin of the overall project. They can simulate over that project. They can do what if my clinical batch fails spec, what's my mitigation strategy? What if I've got to execute this project with only 80% of resource? And you can simulate over the top of that, and then you can prioritize the work. So we prioritize some work for a formulator. It's a unit operation and a focus area in the same interface. Now you can engage in multi-agent reasoning, and you can have multi-agent reasoning help you model and simulate over the top of your scientific model now, and recommend conditions to meet your requirements, your output. And then you can introduce your business processes, so you can invite your expert statistician into that very same workflow and the very same interface to have their expert input, and you capture the reasoning and you capture that decision within the workflow. Nothing is escaping the workflow. When everyone's happy, you can collapse that down into the string, and you can send that to the execution layer. It executes across labs and locations and equipment layers. You can very quickly build an experiment that could take weeks to execute across multiple teams and experts. It's quite frightening. But then you can orchestrate that with the lab execution across the people and the automation. You can capture the deviations, capture the chain of custody, capture the context, so that when the data comes out of the lab, it comes with the context that you need. You can feed it back into the models. You can refresh the recommendations because the data has context. It has all the context it needs. So we're closing that learning loop, but we're not closing the loop in a work cell. We're closing the loop up that scientific hierarchy, up through the unit operations, up into the portfolio at that level of closed loop learning. And so separating the platforms there, allowing them to be experts, allows us to really join together the people, the systems, and the data in the way that actually brings that business value and the scientific value. Right, how are we doing? What have we actually built? So far, we've broken down our messy reality and our workflows and our practical work through the labs into atomic tasks, and we've built the simulation. We can simulate experiments across the equipment and across teams and locations, and it's quite good fun. It's a bit like SimCity, it's good fun. We've partnered with Biosero around that artifact, and we have got our first full block traversing from our choice of user interface all the way through the system to lab execution. So the interesting thing is obviously, because this doesn't care about geography, when we run demonstrations, we have our user in North America and the lab execution in Europe when we run our demo. The other interesting thing is because the user can instantaneously onboard their intent, their block that we've given them, and then the execution can happen immediately. So there's no onboarding time. It's about that quick. Right, what do we need to do next? So now we need to build more blocks. We're in the process of building more blocks. We're testing to make sure they run reliably, and then we can put these into practice in the pilot labs. Right, so where have we got? Right, integrating science and technology, keeping science at the forefront of what we do. That is our deliverable, that is our value. So we've got a system, an interface where scientists can onboard their intent directly into the system. They don't have to worry about the automation layer, and they can do it immediately. We've got workflows. We can span teams and labs and locations. We can orchestrate manual and automated tasks and interleave those in the labs. We've got the different dispatch modes that allows us to accommodate different laboratory environments and onboard new automation hardware as it matures, and we can make use of it in our workflows. And we've got traceability of every human action, so nothing escapes the system. We're building it deliberately agnostic to work streams, so that when we scale, we don't have to go and scale linearly by building out one work stream after another. We can scale in a non-linear fashion across work streams just by adding in a few more blocks. And when the work streams change, we can adapt at the user interface level. Okay, so the idea is to bridge our messy reality and our work streams and what we do for a living, our products, with orchestration and automation in a way that we can extract the value into the business and into the science. So structuring the technology and the science together in that way, that allows us to keep deliberate choices over the technology we're using. We can have expert technology where it is expert at. And we're integrating the science and the technology. We believe this is where the industry is headed, because we're keeping everything modular, we're keeping everything agnostic, we're deliberately building so it's scalable, and we're also building it so it's future flexible as well, so it de-risks any integration complexity, whether it's a system or a person or hardware and equipment. And in doing this, we can take our labs and transform them much more expediently, we believe. Good, okay. That's me done. This is the team that did it. I've got a minute spare, I think. So this is the team that did it. I'm not going to tell you which company they work for. You can work that out for yourself. Interestingly, half of these are sponsors. The team is very small. Just the right people doing just the right stuff. Very good. And that's me. I think I can hand over to Ash.
Hello. I'm Ash. As introduced before, I'm the FAS team lead here at Europe. And over the last 10 years, I've been on a journey within our industry. So in that time, I've worn many hats. I've been a customer, and now I represent Biosero. So today, I wanted to talk through what I've learned over the last 10 years, some of my failures, and how I am trying to be better. Okay, so I'm going to start this presentation off by quoting a very wise man and telling a bit of a tale. So let us jump back in time to a fresh-faced, less beardy me. Just finished university, and suddenly I have a very scary bank loan, and I need a job. And I find that job. It's the first day of that job, so now the scene is set. So I'm being shown around the site where I now work. One of the more senior scientists at that company, he's showing me around, and we're going from lab to lab, and room to room, and suddenly we are in a very dark room, and it's clearly not being used. And in this room, I see an elephant. Of course, not an actual elephant, but rather a massive automation platform. It's clearly gathering dust, it's clearly not used. And right there, right then, I promised myself, if given the opportunity to create such an automated workflow, I would never, ever, ever be the one to create an elephant. And what do you know? Just a few years later, at that same company, I was given the job to create that workflow. So good job past me. The powers that be, they gave me the semi-small and very low to the ground task of become the market leader for engineered cell lines. And that sounds pretty easy, right? I mean, especially considering we had very, very minimal capabilities to start with. So me and a group of very smart people, we sat around and we thought about this problem, and we produced what we all thought was a pretty grand plan. So in this grand plan, we wanted to adhere to scientific best practice. We wanted to establish a parallel manual pipeline, not only to add redundancy and avoid downtime, but also so struggling clones, they could be removed from the high throughput pipeline and reintroduced later when it's appropriate. We wanted to identify both instruments and a scheduler that aligned with our needs. Honestly, I thought we'd considered it all. And 3 years-ish, it seemed very reasonable to establish literally everything from nothing, right? Wrong. We took our grand plan to the powers that be, and it was rejected. We had to cut back, specifically to reduce cost and reduce timeline, which I guess is fair. So we rejigged the plan, and yes, we made some compromises. And then in the 11th hour, another tiny addition was made, and suddenly we have duplicate platforms. One here in Europe, one over there in America. And yes, we drifted somewhat from my original proposal, the grand plan. But this version of the plan, it was approved. And oh boy, did we deliver on that plan. We installed those two platforms, one in Europe, one in America. SAT came, SAT went. We worked to commission both the work cells, get the end users trained, and we got both work cells operational. Now, we jumped forward in time. I've since left that role. I've joined Biosero, and I've since developed and installed many work cells, many systems. But out of all these later work cells, the one I think about the most often is my original work cell. So with the almighty benefit of hindsight and a little bit of extra experience, let's explore the first system I designed and ask, was it successful? But because this is the first work cell I designed, my child, if you will, I'm going to be a little bit defensive. So let's actually check in on what success is. So according to the Oxford Dictionary, success is the achievement of a desired result or outcome. And that sounds about right. So let's look at the platform from different views, wearing different hats. So as a customer receiving a product, I got exactly what was commissioned, like to the letter. Now, as a representative of Biosero, looking back, I can see that Biosero provided all the capabilities as written in the statement of work. But now if we look at this with the problem statement in mind, did this platform allow us to become the market leader for engineered cell lines? I mean, for sure, the platforms enabled massive, massive scale-ups. But did these work cells propel us to the status of market leader? Probably not. And I know based on feedback that the work cells right now, they're barely used, or at least not in the way that we intended, with some sections just gathering dust. So I think ultimately, no. The platforms that I worked several years of my life to bring to life, they weren't a success. And that's really sad, really sad. But what's sadder still is that I fell for the trap. The trap I swore I would never, ever fall for. I created an elephant. So yes, we've established that I created an elephant. But what could have been done to avoid elephantation, a word I made up? And what advice can I give to any of you, whether you are really experienced or just setting out on your own automation journey? So with the experience of my own failings as a customer, and with my experience gained at Biosero, I've identified several areas that I could have been better in. These areas. So let's dive into these points. So thinking back to the problem statement, become the market leader for engineered cell lines. We looked at this from a sample and a hardware perspective. How do we handle these cells in a well? How do I process this plate? Is this instrument suitable for our throughput requirements? And of course, these are all really important questions, important aspects of the whole. But the one thing that we really failed to acknowledge sufficiently was the data. The only data we really did acknowledge was data that was critical to driving the workflow forward. So time and date of events, confluence data, things of that ilk. Ultimately, we dissected the problem and we thought we needed to scale a physical process without any real consideration for how we would manage and process this greatly increased data. On top of this, we were trying to weave a parallel manual pipeline together with the automated pipeline without any real consideration for standardizing the data between these two pipelines. And at some point along my automation journey, I've come to the realization that it does not matter what the process is. It doesn't matter whether it's biology or chemistry, plates or vials. Every workflow becomes a data challenge. So we're moving on to stakeholder identification. So previously, my colleague, he gave a very interesting talk on the importance of identifying all stakeholders and the potential delays if some of these stakeholders escape identification. He did a far, far better job of describing this than I ever will. I encourage you to find his talk online, and we'll just move on. What are we moving on to? Target audience. So in my opinion, bespoke automation, it should be available for every end user. It does not matter whether that person is an experienced traditional benchtop scientist, a savvy software engineer, or a junior member of staff. Automation can be for everyone, but it's very, very important that we identify which group our end users fall into and we create the experience for them. For example, some people I've worked with, they hate change. They simply hate change, and I get it. Change is very scary. Some traditional benchtop scientists, they need to see data presented in a certain way in order for them to function as human beings. An experienced developer, they might need to see data in a certain format to enable smooth interaction with their machine learning models or their LIMS. And a junior member, they might need more prompts, more guidance along the journey just to give them that confidence to use the automation and champion it. So if we walk back to my own platform, I worked alongside some very, very talented scientists. They literally had no right to be as good or as knowledgeable as they were at traditional cell engineering. But what I failed to ask myself is whether it's fair to expect these people to pick up a solution that wasn't designed specifically for them. Ultimately, it's these end users that we absolutely have to get on side. It does not matter how brilliant or how perfect a solution is technically. If the end users are not championing the system, it will not be successful. Now I want to touch on ambition versus impact. So ambition is obviously a good thing, It ensures our industry continues to grow and pushes the boundaries of what is possible. But I've seen time and time again, companies, they just want the final product. It's autonomous, it's got all the bells and whistles, it's integrated with God knows what software, and its throughput is immense. But people want this final product without the journey. Hell, my own platform as a customer, I feel, falls into this category. And of course, I'm not talking about the journey in a spiritual sense. I'm talking about building up to a final product step by step, growing in confidence as the solution evolves and ensuring long-term success. So walking back to my own pipeline again, cell engineering, it can be very manually intensive at several stages. But the areas that we absolutely should have targeted were outgrowth monitoring and NGS analysis. Attacking these specific areas first would have allowed us to bring automation into the business gradually. Starting small would have allowed us to understand the needs of our end users, establish clear data structure, and build automation-focused internal processes that align with stakeholder requirements. And of course, this stepwise approach, it could delay the deployment of the final products. But with respect to my own platform, this would have been extremely impactful and greatly improved the throughput of our manual process, putting us well on the way to our final goal. So now I just want to touch on development practices. So along my journey, I've seen programs developed as large, complicated, spaghetti nonsense, monolithic programs. Some people might argue that monolithic programs, they're favored due to speedy completion, as you just dive straight into development, and these people, they are wrong. Monolithic development practices, they result in code that's difficult to test, difficult to maintain, and workflows that are difficult to recover. But we can escape these monoliths. One approach is to attack the problem through intelligent architectural design, dumbing down super complex processes into smaller modules. We're thinking Lego bricks. Each brick has a defined shape, a very clear connection interface. Each brick works independently, but can be combined in multiple ways to build something far more complex than any single brick could represent alone. And this is how we aim to develop our Green Button Go programs. We start with a statement of work and spend time upfront to translate your processes into modular GBG programs. And then we can take it one step further. We can build complexity from this simplicity. Using our orchestration catalog, we can weave together simple brick programs into complex and robust workflows. And this would be that final product. So here, we've arrived at the end of our journey. Our end users, they're engaged. Our stakeholders, they're identified. Our data structures are established, and the elephant, it's been avoided. So thank you so much for listening to me. Thank you for listening to the other speakers. If there's any questions, come see us at booth 411. Thank you.